Dr. Όθων Ρεντινιώti is leader of the team that's developed this robot fish. He's an associate professor in aerospace engineering at Texas A&M. He joins us from College Station, Texas. So, Dr. Rεντινιώti, how does this, what would you call it, mechanical fish, robot fish, how does it work?
Yeah, I guess the official name is biomimetic underwater vehicle. It works, it basically mimics the fish motion. And it's doing that by using a new technology. It's called shape memory alloys that basically contract and expand as you change their temperature. And they do that with an associated large force and strain. So what we do is we actually make a spine for the vehicle, just like our own spine. It's got vertebra, it's got several segments, and each segment is joined with the adjacent segments through those wires. We call them the SMA, or shape memory alloy wires.
So could I just pick up on that? What are shape memory alloys?
It's a nickel titanium alloy. Typically 50% nickel, 50% titanium. And they go through a phase, what we call a phase transformation. As you heat them up, say from ambient temperature to about 70 degrees C, they change phase. And this is associated with a large change in length of the wire. And then when you cool them down, they go back to their original length. So this property can be used for actuation.
So if you want, so if they're going to actually move the body of this thing, do you have to go heat, cool, heat, cool, heat, cool really quickly?
Exactly.
How do you do that?
We do the heating electrically through resistive heating, and we do the cooling by embedding the SMA wires into little small channels through which ethylene glycol circulates in a controlled manner. So both heating and cooling are controlled through an adaptive algorithm, basically, that runs online.
But how fast then can you get these body segments to move, given that you have to heat and cool them to do that?
Okay, the wires themselves, if they don't really have to move a lot of load, we have been able to get them up to about 20 oscillations per second.
Wow.
When we actually mount them on the vehicle, we have been able to go to 3 or 4 cycles per second.
So 3 or 4 times back and forth every second?
Yes.
So how fast could a robot fish move at that kind of rate?
Well, it's a difficult question to answer right now, but I would guess with our calculations, it would be several body lengths per second. This is typically the unit that is used in aquatic propulsion.
Now, why go with this, I guess, as yet unproven technology when I suppose you could just use motors?
One of the benefits is the fact that you have higher power densities. In other words, for smaller masses of the material, the SMA material, you can get the same kind of actuation in terms of amplitude or stroke and force. So you can get the same motions with a lot less mass of the material. Therefore, you can leave a lot of the internal vehicle space open for useful payload. That's one thing. The other thing is that there is a lot fewer moving parts. And this is a good thing because any moving part produces an acoustic signature. And an acoustic signature, as we know, in an underwater environment is crucial, and it's actually detrimental because it can be detected from enemy vehicles. And one other thing is the vehicles that mimic the motion of fish leave a wake, which is the flow that they leave behind them, which is a lot less detectable than the wake the conventional propellers leave.
I see. Where did this technology, the shape membrane alloys, come from?
The alloy itself was put together several decades ago, I think in the 60s, but it was only recently that it actually kind of was resurrected, and people are studying them. And the reason for that, one of the reasons was the fact that they're very hard to model. Their behavior is very hard to model. They're what we call nonlinear hysteretic materials, and you need a good model for the behavior of the wires in order to have successful control. And only recently this has been actually achieved.
So what sorts of submarines would the U.S. Navy or would anybody interested in applying this technology be looking at?
There's right now, of course, the jury's out, but there is several potential applications, starting from unmanned underwater vehicles to actually manned submarines, where, let's start from the underwater vehicles. We could have several applications for those. For example, oceanographic studies, study of temperature gradients or salinity, or ocean currents, or mapping of the ocean floor, demining that the Navy might be interested in, tracking other submarines would be another one, and the fact that those vehicles will look like fish, will act like fish, and such they will be stealthy. They would be hard for other enemy submarines to detect them.
So, and you mentioned that they might even be manned. So is this technology, can this technology be scaled up to large vehicles?
Sure, it can. The only problem right now, which is not really a big problem, is that it seems like everything is moving when the fish is actually flexing its muscles to propel itself. It seems like that everything is moving, but that's not entirely true. There is a section of the fish which is around quarter of its length, measuring from its nose, that has minimal motion, in which
that's where you'd have to sit.
Put the people, yeah.
Well, it's a really neat technology. Thanks for telling us about it.
My pleasure.
Dr. Όθων Ρεντινιώτη is an associate professor in aerospace engineering at Texas A&M. He joined us from College Station, Texas.